Okay, hello class. We proceed to the next part in this chapter. Okay, previously we have learned about the concept of equilibrium in the reaction. What is the criteria for the equilibrium in the chemical reaction? Firstly, we covered on the correlation between the mole fraction to the reaction coordinate, or otherwise, if the reaction in the equilibrium, the reaction coordinate also known as the equilibrium conversion. So the equation or the correlation is based on the yi. So if the reaction in the vapor phase, otherwise we can replace to si. So yi equal to ni naught plus the stoichiometric number for the species I times the reaction coordinate over n naught plus v reaction coordinate. If the reaction in equilibrium, so it turns to vi, or this is the equilibrium, the conversion at equilibrium, and n naught plus v, the conversion at equilibrium, or the maximum conversion. So same goes to the liquid phase. We can use the same correlation but replace to the symbol of Si. And then for the multiple, okay, if we have multiple, so we can use the same expression but replace to the total summation. So Vi, okay, at the reaction, number of the reaction and the reaction coordinate over n naught plus summation of the Vj. Okay, so this is the how we introduce the number of stoichiometry and also the reaction coordinate to the multiple reaction. And then we also learn about the how to correlate with the equilibrium constant to the effect of temperature. Okay, we have learned about the two important equation in obtaining the equilibrium constant. So we have minus ln K equal to delta G, or the change of the Gibbs energy at standard over RT. And then we can also expand this equation to the G at reference temperature. Usually we use at 298 Kelvin minus delta H, the standard at reference temperature, over RT naught plus delta H over RT plus 1 over T naught T delta Cp over R dTn plus T naught to T delta Cp naught or standard over R dt over T. So this standard can be obtained from the table C4. And this is the Cp value can obtain from table C1. We have learned about the effect of the temperature to the equilibrium constant from the previous part. Okay, today we gonna learn about the relation of the equilibrium constant to the composition by define and investigate at gas phase reaction and liquid phase reaction. And then the last topic is to relate with the equilibrium conversion for the reaction. So we will learn about the definition and also how to determine the equilibrium conversion for the reaction. So equilibrium conversion is denoted by the epsilon E for the single phase, and if the reaction heterogeneous system. Okay, the first topic is to correlate with the equilibrium constant to the composition. So in the gas phase reaction, okay, for the ideal gas law is stated for the pure gas at the standard state pressure, and the pressure P naught or the standard is at 1 bar. So the fugacity of the ideal gas will be equal to its pressure. So this is from the what we have learned previously, the fugacity of the species in the solution over the fugacity of the species by the power of the stoichiometric number equal to the equilibrium constant. Okay, since for the ideal gas, the fugacity of the species will be equal to the pressure. So we may replace it to the pressure. And then for the real solution, so we introduce the fugacity coefficient into the fugacity of the species in the solution. So replace it to the fugacity of the species in the solution to the introduce the activity, its activity, and then it gives another equation. So example, if we have F is the fugacity coefficient for the species in the solution, example species I, times its mole fraction of P, and also we have P naught. This is P. Okay, for the ideal solution, we can replace the fugacity of the species in the solution to its species. So we can have Yi P over P naught P, and then we can rearrange this expression to obtain this expression. So the mole fraction to the times the fugacity coefficient of the species I and its number of stoichiometry equal to P per P standard, the power of minus the number of stoichiometry and K. Okay, for the low pressure, the fugacity coefficient is equal to 1. So we can have this final equation or the submission for the species, for each species equal to P over P naught or the P standard and the power of minus P or the number of stoichiometry times equilibrium constant. Okay, P naught usually or the standard is equal to 1 bar. So P is the pressure in the system, and then this is, since this is for the gas vessel, so we gonna have the or denotes by Yi. Okay, from this equation, we can summarize it by derive this equation to this explanation. Okay, example, if we consider based on the change of heat, because when we talk about the reaction, in the reaction, it can be endothermic or exothermic. Okay, for the endothermic, that means we absorb heat into the reaction, and the sign of the delta H standard is positive. And then if we increase the temperature, the equilibrium constant will be increased. Okay, referring to this expression, by increasing the equilibrium constant, so the submission of the mole fraction to the power of stoichiometric number also increase, and then the reaction will be turned to right, because we have example A plus B equal to C plus D. Okay, for the endothermic, that means we plus heat into the reaction, so the reaction will be turned to right, and then eventually it will increase the equilibrium conversion. Okay, for the endothermic, we're gonna have the negative sign. Okay, as increasing the temperature, we will increase the equilibrium constant. So increasing the temperature, reduce the equilibrium constant. So it will reduce as well the mole fraction to the power of a number of stoichiometry, and then the reaction will be turned to the left, because for the isothermic plus here, and then it will reduce the equilibrium conversion. Okay, so if the reaction is to increase the efficiency of the reaction, it will depend on the equilibrium conversion. So if we have higher equilibrium conversion, so eventually we gonna have this higher yield in the reaction. So next is based on the stoichiometric number, because for both them we have also introduced the stoichiometric number in this expression. Okay, if the number of stoichiometry is negative, so if we have negative value, so when we increase the pressure, the mole fraction also increase, and then the reaction from the left to right, and also we will increase the equilibrium conversion. Okay, for the positive stoichiometry, so if we have positive of the stoichiometry, so once we increase the pressure, it will reduce or decrease this side. So when we decrease this side, that's mean the reaction to turn to the left and decrease the equilibrium conversion. Okay, estimate the maximum conversion, or the denotes by epsilon E of ethylene to ethanol by vapor phase hydration at temperature is given at 250 degrees Celsius or 52315 Kelvin, and then temperature, okay, pressure at 35 bar for initial steam to ethylene ratio of 5, so 1:1:5. Even the fugacity coefficient, okay, the fugacity coefficient also given. Ethylene C2H4 0.977, H2O is 0.887 and ethanol is 0.827. Okay, K also given. How can we correlate with the maximum conversion to the K? So, and also the next is to evaluate the impact of the conversion if operating pressure is further increased. So, if we further increase, what is the impact of the conversion? So we already extract all the information. So how can we determine the maximum conversion by given all this information? Okay, if the question is operate at lower bar, so we can assume that this is an ideal condition. So you may neglect the interaction among the species, and also this fugacity coefficient can be neglected. But since the other reaction is operate at higher pressure, so we must consider the fugacity coefficient. Okay, if the question is not given the fugacity coefficient, so you may calculate the fugacity coefficient using the equation or state using a virial or the Lee-Kessler. So this is how you determine the fugacity coefficient for each species. You may try this first, and then at the same time, I will show to you how to solve it. Try to correlate with the equation that we have learned in the gas-phase reaction. Okay, how to solve this problem? Since this is a gas-phase reaction, so we're gonna use this expression for the non-ideal gas by introduce the fugacity coefficient of the species. So from this expression, the fugacity of each species is given. We can obtain the stoichiometric number for each species, and then the pressure also given in the problem. So P naught of P standards is equal to 1 bar. So for this value, the total V or the stoichiometric number also given, and K also given. So how can we correlate with the mole fraction to the conversion? So we have learned about the mole fraction equal to Ni naught plus, since this is a single reaction, so it plus Vi, the reaction coordinate, and also N naught plus V reaction coordinate. Okay, the expression of this mole fraction is based on the reaction coordinate, or we can also replace this reaction coordinate to the conversion. It has this same concept to the conversion of the mass equilibrium conversion. So this is denoted by E or the epsilon E. We need to express the mole fraction for each species. Okay, let me write up the reaction. Okay, the ethylene, we add with the water in a gas phase equal to produce the ethanol. So in gas. So the ratio is given, so we can presume this is for the number of mole. So for the ethylene equal to Ni or Ni naught is 1. So this is the minus 1, and plus 1. So minus this equilibrium conversion over the N naught is 6, 1 plus 5, and then we have plus, this is all this minus 1, so minus the, okay, we have 1 minus over 6 minus the maximum conversion. Okay, next is YH2O. So this same, so we have 5 minus over 6 minus, okay, the maximum conversion. And then for ethanol, we have 1, but the initial is not provided, so we consider is 0. So we have this maximum conversion over 6 minus the maximum conversion. Okay, the next is to insert this expression for each species to this equation. So this is the first step, and then the second is to insert. Okay, so we have product over the reactant. So the product is ethanol. So YC2H5OH times its fugacity coefficient is, the value is 0. Okay, maybe I should write at this first. Okay, the fugacity of ethanol equal to 0.927. Fugacity of ethylene is 0.977. The fugacity of water is 0.887. So by inserting this fugacity is 0.827 over the ethylene is, okay, so we have the ethylene is 0.977, and then this supplementary is minus 1. We have this plus 1. And then we have for the H2O is 0.887 and minus 1. So equal to P over P naught is 35 bar. So we have minus, so it turns to 1. And then K is 10.02 power of minus 3. So the next is, so we have this expression for the ethanol is minus 6. Okay, and then it's 0.827, and then over the expression for ethylene is 1 minus. And then we have this 0.977. And we have this one. Minus 0.827. 887 minus 1 equal to 35 plus 10, 0 to power of minus 3. Okay, so we have now is the number 6. 6 minus 9 of 5. Okay, this is to simplify this. So you replace all the value to the right side. So we have 0.887 times 0.977 over 827, and then 35 minus 3. Okay, from this we can expand the expression. So you solve this over 1 5 minus the maximum conversion equal to 0.367. And then we have, here I need to 6 the maximum conversion plus square equal to 0.367, 1, and also we have 5 minus the maximum conversion. So you expand this to give you a quadratic equations. Plus 1.342 equal to 0. So using your scientific calculation, so you can obtain two values, which is the first is 5.767, and then second is 0.233. So comparing between the both values, so we gonna choose the root equation is less than 1, because the conversion, when convert into the percentage, it shouldn't be higher than 1. So when we convert into this percentage, the percentage of the maximum conversion in this fraction is 23.3%. And then this is the value of this maximum conversion. Next question is to evaluate the impact of the conversion if we further increase the temperature. Okay, by referring to the example in the previous part, example 13.4, we have evaluated the same reaction by the effect on the temperature. So at 480.15 Kelvin, okay, so the equilibrium constant is equal to 1.443 power of minus 1, and at temperature of 593.15 Kelvin, so the equilibrium constant is 2.942 power of minus 3. So we can see as increasing the temperature, the equilibrium constant will be decreased. So this is for the, it shown the effect for the exothermic. Okay, for the exothermic, so we can say that as temperature increase, the increasing of the equilibrium constant eventually leads to the decreasing of the conversion. So in obtain the higher conversion, so we should operate the reactor at lower temperature, or it can conclude by this sentence. In this reaction, increasing temperature will be decrease the equilibrium constant and also decrease the conversion. So to improve, we just to operate it at lower temperature. Okay, for the liquid phase reaction, okay, for a reaction in the liquid phase, the expression is the submission of the species or the fugacity of the species in the solution over to its standard by the times the power of the number of stoichiometry equal to the equilibrium constant. Okay, we know that the fugacity of the species in the solution equal to its activity coefficients times the mole fraction and also the fugacity of the species. And then by replace it to this expression, so it gives us the ratio of the fugacity of the species to the fugacity of the standard, which we can correlate with from the differentiate between the gifts of the species to the gifts of the species as standard. Okay, and then integrate this expression, it gives us this equation or known as the binding factor. Okay, at higher pressure, the exponents equal to 0. If we have higher pressure, that means the exponents should turn to the exponent 0 equal to 1. And then we can have this expression for the ideal solution. The activity coefficient is equal to 1, and then it gives us another important equation to be introduced to in the liquid phase reaction. Okay, this is for the ideal solution, but for the non-ideal solution, we introduce the activity coefficient into this expression to obtain the equilibrium constant. Okay, this expression known as the law of the mass action. Okay, since most of the liquid is in the non-ideal solution, or in the real system, we consider on the interaction among the species, or known as the non-ideal solution. So basically, this expression can be expected to have a pure yield result. So for the non-ideal solution, you may use this expression that by introduce the activity coefficient into this expression. Okay, let's take a look on the example for the liquid phase reaction. Okay, acetic acid is esterified in the liquid phase with ethanol at 100 degrees Celsius and atmospheric pressure to produce ethyl acetate and water according to this following reaction. If initially there is 1 mole of acetic acid and then 1 mole of ethanol, estimate the mole fraction of ethyl acetate in the reacting mixture in equilibrium. So the given information is at 100 degrees Celsius or equal to 37315 Kelvin, and then pressure is at 180 M. And what else the other information? So the number of mole, and note for the acetic acid and the ethanol also given, and we need to estimate the mole fraction of ethyl acetate. So as ethyl acetate, what is this? A mole fraction for ethyl acetate. Okay, since the reaction is operate at lower temperature and pressure, so we can conclude the reaction in ideal solution. Okay, first we already extract all the info. And then second is to define which appropriate expression, define the expression or the equation to solve this problem. So to estimate the mole fraction, so we have this as I, the Pi equal to K. So the value of K is not given, as well as the mole fraction. The first is to determine the equilibrium constant. So the equilibrium constant at 373.15 K. So what is the value? So we can correlate this equilibrium constant using this equation or the expression K 37315 over the reference is at 281.5 equal to minus delta H at 215 over R, and then 1 minus 37315 minus 1.29815. So we can use this expression to determine the equilibrium constant at 373.15 Kelvin. Okay, this equation can be used at lower temperature. Okay, the first is to identify which value should be obtained. So we have we can obtain this from table C4, and then this also done. And then how about, okay, so we have two unknown value or the equilibrium constant at both temperature. So we need to obtain first at 298. So using the equation of ln K equal to delta G standard over RT. So we can obtain the value of equilibrium constant at 298 by determining the delta G standard at 298, which we can refer this from the table C4. So from table C4, okay, so list all the species first. So we have delta, since we need to obtain to be inserted into this equation, and then delta G to be inserted into this equation. So we have species, we have acetic acid as the reactant, react with ethanol to produce ethyl acetate and also the water. So for the from table C4, so I just list this value. $480,000, and then for water we have 295,830, and then for delta G we have 900, and then 174,780. We have 303 and also 200, and then we have 273,129. Okay, we start with this value to obtain the equilibrium constant at 298. So, and then next we need to determine the delta G at a standard for all the species. So delta G standard equal to the product minus reactant. So the product is, first we have ethyl acetate, 332,200 minus water 2,129. So we have the reactant is acetic acid and ethanol. Since based on the stoichiometric number for the reactant, so we have -1. So we gonna have, eventually we have plus 289, 900 plus 100,074 and 780. So the value for the delta G is minus 4,650 joule. And for the delta H at 298, so insert this value. So we have minus 480,000 minus 285,000, and then plus, okay, by considering the stoichiometric number, so it turns to positive 484,500 plus 277,969 equal to a minus 3,640 joule. So inserting this value to this expression, so we can get minus ln K 298 equal to, the value is minus 4,650 joule over 8.314 joule per mole K, and then we have 29 8 Kelvin. Okay, since this is the reaction, so we gonna insert per mole to the value of change of the standard Gibbs energy. So this, it gives the value of equilibrium constant at 298 equal to 6.5299. And then the next is to determine the K, or the equilibrium constant, at 373. So by using this equation, we have K 373.15 over 6.5266 equal to minus, okay, what's the value of delta H is? It turns to positive 3.640 joule over R is 8.314 joule per mole K, and then this is based on mole as well. So 1 over times 1 over 373.1K minus 1.398.15K. Okay, this is based on per mole. So we can have this, the value of K at 373.1K equal to equilibrium constant at 373.15 equal to 4.8586. Okay, so we already have this value from this expression. Okay, for the next is to determine or estimate the mole fraction. So we have this based on the total of the SI, VI equal to K. So use this expression. We already defined the value of K at 373 Kelvin. So first we start with the to obtain the mole fraction, or the mole expression of the mole fraction. So from the equation, we have this acid or acetic acid liquid plus ethanol liquid to produce ethyl acetate C2H5 liquid plus H2O also in liquid. So we, okay, this is minus 1, plus 1, plus 1. And then we, how can we express this? We have 1, 1 for the ratio. So we can correlate the expression based on the mole fraction. Since this is a liquid, so Si equal to Ni naught plus the, for this stoichiometric number of the species I over this over the N naught plus V, the reaction coordinate. So start with the acetic acid equal to the ethanol as well, because it has the same initial number of mole and also the stoichiometric number. Okay, equal to Ni is 1 minus the reaction coordinate over N naught equal to 2, and then the total stoichiometric number is 0. 2 minus 2 equal to 0, so it turns to 0. How about the product? So we have the same stoichiometric number, so eventually it's gonna have the same expression for the mole fraction. So for the ethyl acetate equal to the water, and the for the initial is not given, so the reaction coordinate over 2. So insert this expression to this equation. So we have product over reactant. Product is over 2, and we have over 2. we have 1 over 2, 1 over 2 equal to, okay, K is 4.8586. So we have this H square over 4.8586. So for the quadratic, so you solve for the quadratic, it gives us the decimal conversion is equal to 0.6879. And then insert this value to this expression of ethyl acetate. So to this expression 1 to this expression of 2. So we can get the mole fraction or the estimate of mole fraction for the ethyl acetate equal to 0.344. Okay, this is how you solve this problem. So in summary, for the liquid, so please ensure whether this is non-ideal or ideal solution. For the ideal solution, we can conclude this is in ideal solution if it operates at lower temperature or the molecule is not interact each other. But for the non-ideal solution, we introduce the activity coefficient into this expression. Okay, next we move to the equilibrium conversion of the reaction. So in conclusion, the equilibrium, that means there is no tendency for the change to occur, whether by the mass transfer between phases of the chemical reaction. Okay, for the single reaction in a homogeneous system, we can use a straightforward solution if the phase is assumed to be ideal gas or ideal solution, but ideally it's not possible. So we should use the computer through the application of state to solve the problem. Okay, for the heterogeneous system, which in the reaction it having one more phases, it more complicated. Okay, this is the summary of the expression that can be used for the single reaction to express the mole fraction. Okay, if the reaction in the gas phase, so it denotes by Yi, but if the liquid phase, you can replace it to Si. And for the multiple, you can use based on the submission of the stoichiometric number to the reaction coordinate or the equilibrium conversion. And the second is to obtain the equilibrium constant. We can use this equation. And to relate the equilibrium constant to the phase of the reaction, so you can use this equation or this described in the 3. So for the gas phase reaction and the non-ideal, we introduce the fugacity coefficient. And for the ideal gas, there is no introduction of the fugacity coefficient into the expression. And for the liquid phase, for the non-ideal, we can use the activity coefficient. And for the ideal solution, the activity coefficient is not considered to determine the equilibrium constant, or if the question is speaking about the mole fraction. Okay, for the heterogeneous system, okay, example, if we have the calcium carbonate to react with the calcium oxide and the carbon dioxide, so the equilibrium constant, or if we can use based on the whether the concentration or the if the for the gas phase, so we only consider for the carbon dioxide. Okay, the heterogeneous equilibrium reaction is the equilibrium reaction in which the reactant and the product are not present in the same phases. Okay, the concentration of the pure solid, okay, this is the pure solid, and pure liquid will be not included in the to express the equilibrium constant, because the concentration may remain the same throughout the reaction process. Okay, the reaction in the heterogeneous reaction system, when liquid and gas phases are both present in the equilibrium mixture of the reacting species, both VLE criterion and chemical reaction must be satisfied. Okay, these are the example. Okay, we can use several approach to solve the problem by either by consider the reaction occur in gas phase, and then the equilibrium constant will be evaluated based on the delta G standard at either gas state or at 1 bar and reaction temperature, or the reaction may be considered occur in the liquid phases and it based on the delta G at the liquid or the standard state in the liquid phases. Okay, for the reaction occur as written in the reaction involving involve both phases, so the delta G can be evaluated by using a mixed standard state, which is the C here is an ideal or 1 molar equation or 1 molar aqueous solution, and B as pure liquid and A as pure gases. Overall, the method theoretically leads to the same equilibrium composition provided Henry's law applied to species C in the solution is valid. So we can apply either consider in the gas phases, liquid phases, or mixed phases based on the written in the reaction. Okay, for the multiple equilibrium, okay, multiple, that means we're gonna have a multiple reaction. So these are the general equation, and then for the gas phase, it replaced by P standard, and then for the ideal gas, we can use this expression. But for the multiple, it has this stoichiometric number based on the number of the reaction. Okay, this is the summary to determine the equilibrium conversion for the multi-reaction. Multi-reaction, that's me example, we have A plus B equal to C plus D, or another reaction is A equal to C plus D example. So we have two reactions. Okay, the first step is to build up the relation of the mole fraction to the conversion. And then after that, tabulate the data to using the equation of the ln K equal to delta G over RT equal to delta G minus delta H over RT naught plus delta H naught over R plus 1 over T naught GCP delta CP over R dt, and we have a plus T naught T desired delta CP over R dt over T. So this is the expression equal for the equation 2. And then after that, substitute the expression of the mole fraction and also the equilibrium constant that we obtain to the equation 3, whether the phase of whether the gas phase or liquid phase. So we need to consider none whether for the gas, if the gas phase or the reaction in the gas, whether it is the non-ideal or ideal state. Same goes to the liquid. You should find the reaction whether this is non-ideal solution or ideal solution. For the non-ideal solution, we're gonna introduce the activity coefficient in the expression. And for the ideal solution, we're gonna neglect the activity coefficient. Same goes to the gas. For the non-ideal solution, we introduce the fugacity coefficient into the expression, and for the ideal gas state, we neglect the fugacity coefficient. And then after that, we can solve this equilibrium conversion or the maximum conversion simultaneously, because we have two. If we have two reactions, so we're gonna have two different value. And then after that, we may calculate the mole fraction, and finally we can calculate the equilibrium conversion of the reaction. Okay, how to solve this? conversion simultaneously. So example, if we have we're gonna have two different equations that represent for the conversion 1 and for the conversion 2. Okay, example, if the reaction is A plus B, C plus D, or A equal to C plus D. So we're gonna have two different conversions. So to solve this is using the correlation of 2 equal to the 1. So by replace it into this expression, and then finally we can obtain the value for both conversion. And then after that, you may also using the guess method. Okay, guess the value of conversion for the reaction 2 with this range from 0 to 1, and then calculate the value of conversion of reaction 1, and then substitute into this reaction to obtain or recalculate the conversion of reaction 2, and then we may compare the gas and calculated value until we can obtain the same value. Okay, there are two methods to obtain, whether using this correlation or using the gas value. Okay, for the last, before we end it, to test your understanding, as for assignment, define the Lee-Catelier principle and describe factor affecting the equilibrium constant. Okay, for the next topic, we're gonna learn about the flow sheeting using a Unisim. Okay, before I ending my presentation, let me summarize. In this chapter, we have learned about the equilibrium in the chemical reaction, how we can determine the equilibrium constant by determining whether based on its effect on the temperature and also the composition. Okay, for the composition, we can determine the equilibrium conversion, whether by using in the gas phase reaction or the liquid phase reaction. So in general, you should understand what is the difference between the non-ideal and ideal state for both reaction in the gas phase and also the liquid phase. Okay, by that, I will end my presentation and I'll see you for the next chapter. Bye.